You ready? You guys ready? Are we starting? Hello. Today we're doing a lever arm. And then once I teach you about lever arm, then we're going to start doing more of these sum of the torque equals 0, sum of the force in the x and y directions equals 0 problems. But let's talk about lever arm. So far, here's what you've learned. Okay, and this is intro, so don't write this down. This is just all intro right now. You learned that torque equals the force that's perpendicular to the lever arm times the distance between the torque and between the force and the point of rotation. Okay, that is, you did this sort of thing here. Here's my, let me put it down. Again, this is intro, so don't write it down. Sorry. Here we go. This is the sort of thing you did. If that's your point of rotation, here, let me put this aside, I don't like that marker. And I had some force happening here at some angle theta, okay? And this is some distance d between where the force is applied and where the point of rotation is. You learn that the only component of that force that actually opens this door, turns the door, is the perpendicular component. Only the component of force perpendicular to the lever actually turns the door. The component of force parallel to the lever just gets you a black eye, okay? But this will turn your door, that perpendicular component. And so that perpendicular component, if this angle is theta, then this perpendicular component ends up being force times the sine of theta times d. And so you get the formula for torque that the book has, Fd sine theta. And that will work out just fine for you on most problems, on virtually all problems. Just knowing that formula will be good enough. But the problem is, if you're going to go out into the real world and work with adults, whether it's with mechanical engineers or mechanics, they're always going to be talking about something called lever arm. And you're going to go, wow, never in my life has anyone taught me about lever arm. Well, that won't be true for you guys, because I'm going to teach you about lever arm today. I'm going to teach you about another way to view torque. And where lever arm comes from is this. Instead of saying, okay, torque is the perpendicular component of force times the distance to where the force is applied, we go different. We say it's force multiplied by the perpendicular component of the door. The component of the door perpendicular to force. And that component of the door perpendicular to the force, we call it lever arm. So you're going to learn today that torque is equal to force times lever arm, which lever arm usually gets written as a script letter L. So force times lever arm with a script letter L. Let me demonstrate what lever arm is on a problem like this. What you're going to end up doing is saying, okay, this is the direction of my force, all right? What's the component of this door perpendicular to the direction of my force? And by the way, we're going to learn that there's a name for this green dotted line. It's called the line of action, or the line of force. It's the line that contains the force vector. But anyway, starting from the point of rotation, you're going to draw the component of your door perpendicular to the force, to the line of action. And you're going to go, this guy here, this is my lever arm. By exerting my force in this direction, I'm effectively shortening the length of my wrench. Let's say this is a wrench and you're exerting a force on this wrench to turn a bolt. By exerting your force at this angle, you're shortening the length of your wrench. You're making it so that your wrench is only that long. Now, looking at the trigonometry of this hypotenuse is d, this is opposite the angle theta, so this ends up being d sine theta. So you end up getting the same equation, right? Force times d sine theta. But it's a different way of looking at things, and it's a way of looking at things that will actually serve you well on a lot of problems. So let's go ahead. I'm gonna give you some problems where you get to find lever arm, then I'm gonna give you some problems where your conceptual knowledge of lever arm will help you get right answers instead of wrong answers. So let's go ahead and do a simple find the lever arm problem. Here's example number 1. Okay. Let's say this is a 2-meter door, and I'm going to exert my force here at a 30-degree angle. And I want you to find the lever arm. There's a 2-step process to finding the lever arm. 2 steps to finding L. Step 1 is to draw the line of action. That's the line containing the force vector. The line of action. It's also called the line of force. But like, you know, among adults, among engineers, they call it line of action. So here we go. Here's my line of action. Step 2 is to draw the segment starting at the point of rotation and ending perpendicular to the line of action. Draw the line segment starting at the point of rotation and ending perpendicular to the line of action. So here we go. Starting from here, draw the segment perpendicular to the line of action. Are you guys getting that the lever arm is going to be 2 times the sine of 30 degrees? This length here is 2 sine 30. The hypotenuse is 2, the angle is 30. This is opposite the 30, 2 sine 30 degrees. And so if someone asked me for the torque would be force times 2 sine 30 degrees. Or, you know, the torque would be force times 1 meter. Now, you could have also gotten this by just doing FD sine theta, as long as you make sure your theta is the angle between the actual lever and the force. Don't let anyone fake you out. You guys ready to do it on your own? Here it comes. Example number 2. We'll call this 2 meters. And I'm going to exert my force. We'll go this way. Exert my force this way. And this will be a 30-degree angle. Okay? I'd like everyone to please get me the lever arm now. Draw your line of action. Draw the perpendicular from the point of rotation to the line of action. And get the length of that perpendicular. Good luck. What's your favorite flavor?
It's between cherry and the chocolate.
Good for you.
I haven't tried the lemon one though.
Yeah, I'll have to try it. Lemon, really? 'Cause my favorite is orange. didn't know they had lemon. Oh, well, it's yellow, but sometimes they fool you with the,
It's lemon. Look at the top.
oh, artificially flavored lemon. I'll have to try that next.
I
If
don't
I
know.
like orange, would it stand the reason I love lemon? Is it citrus?
I love citrus fruits.
Oh, me too.
I have grapefruit, lemon, and lime haichu in my backpack.
Wow. For you. I don't even know what that is.
It's a Japanese candy.
Yeah, yeah. I figured it was something yummy, but. Well, I hope everyone's drawing their line of action. Boom, 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 like that. And I hope everyone's drawing their lever arm, which is going to be perpendicular to the line of action like that. And I hope everyone got that if that's 30 degrees and this is 90 degrees, then that makes this guy 60 degrees. Or if that's 30 degrees, then this guy's got to be 30 degrees because opposite angles are congruent. But anyway, that makes that guy 60. So this lever arm is going to be 2 meters times the sine of 60 degrees. How many people got 2 meters times the sine of 60? Good. Did anyone get 2 meters times the sine of 30? Okay. Well, if you got 2 meters times the sine of 30, make sure you got to get the angle between the door and the line of action. Don't get some weird angle measured relative to a vertical. Yes?
I just did 2 times my cosine.
Oh, then you win. Then you're great. Yeah, did anyone do 2 cosine 30? Okay, good enough. That's great. That's beautiful. It's the same answer. It's correct. Okay? Any questions or problems on this? Okay. Then I need to give you a couple more problems involving lever arm. I've got a guy, and this guy is lifting a wheelbarrow. Okay? Wheelbarrow. I've pronounced it wheelbarrow my entire life until I started teaching, and then I encountered the wheelbarrow problem and realized I'd been pronouncing it wrong my whole life. How many people pronounce wheelbarrow correctly? Good for you guys. How many people pronounce it wheelbarrow? Good for you guys. Well, it's wheelbarrow.
Oh,
Who'd have thought? Yeah, I've been pronouncing it wrong my whole life. Wheelbarrow. Well, anyway, so I got this wheelbarrow, and it's got the 500 newtons of stuff in it right there. And the wheelbarrow itself weighs, the wheelbarrow weighs 100 newtons, and the center of mass of the wheelbarrow is right there. This is the center of mass of the wheelbarrow. And this distance from there to there is 0.8 meters. This distance from there to there is 0.3 meters. Okay. And we want to find the force up that the guy exerts. Find the force up that the guy exerts. Well, what do you suppose step 1 is going to be? Thank you very much, Imani. You've made me very happy. Thank you. What is that on your shirt? London Calling? Oh, good for you, The Clash. I was watching old videos, and there was should I stay or should I go? I love The Clash.
I
Yeah.
should go.
Okay, great. So let's do a free body diagram. So here's my wheelbarrow, just like this. Okay. What's one force acting on this wheelbarrow? What?
The 500?
Good, the 500 newtons that's acting right here at the end. 500 newtons down. What's another force acting on the wheelbarrow?
The guy pushing it?
Sure, the guy, he's not pushing it, it's not moving, so he's
Oh.
just lifting it.
Above and below.
So you guys okay that all he's doing is lifting it, and we'll call that F? What's another force on the wheelbarrow?
The 100.
Sure, the 100 acting at the center of mass of the wheelbarrow. Okay? So maybe I should make this a little longer because it is 5 times bigger force. Okay? And there's one more force acting on the wheelbarrow. What's that? We've got that already, 100 newtons. What's the other force acting on this wheelbarrow? Normal force where? Where's this normal force acting?
The wheel.
Yeah, where the wheel is. So we've got normal force up. We've got a normal force up. So there it is. There's my forces. This distance from there to there is 0.8 meters. This distance here is 0.3 meters. So now it's time to do sum of the torques equals 0. Tell me, which point would you like to take your torques about? Remember, all I want is the force that the guy exerts.
Or normal forces?
Thank you. Imani says where the normal force is. Why would she say that? Why would she say something so crazy? Yeah, Sean.
Because when they cancel.
Thank you. They'll cancel. They may not cancel. I mean, they may be different forces. They are. But the point is, I don't know what the normal force is, and do I care what the normal force is? No, not at all. So shoot, let's just take our torques about that point, and now the normal force and the 500 don't even enter into our calculations. Well, now here's the interesting thing. I need to do FD sine theta. Have they told me what theta is? Do I have any way of finding what theta is? No. Can I get the components of force perpendicular to the board? No, because I don't know what theta is. So how am I going to do this problem without theta? Have they given me something that'll still allow me to do this problem? Yes, Fatima? Yeah. Tell me more.
Will they tell you like how far apart all the forces are, so you know the total distance of the...
Okay. But tell me more. Someone besides Fatima, tell me, what is this 0.3 for this 100 Newton force? What name do I give this 0.3 meters? Yeah, look. Wait, didn't I say someone besides Fatima? Yeah, you guys okay with that? Lever arm? Do you see that they didn't give us any way of finding theta? They didn't give us any way of finding perpendicular components of force. All they gave us was lever arm, right? Because here's the line of action, okay? And here is the perpendicular segment from the point of rotation to the line of action. Hey, guess what? That's my lever arm right there, you know? You guys okay with that? This distance from here to there, the 1.1 meters, that's my lever arm. That's the lever arm for this force because the line of action acts like this. Oh, I should have done, I always like to do my line of actions in green. So the line of action goes like this, okay? And then you've got your lever arm. So this is a problem. This is like number 15. You're going to get problem number 15 on tonight's homework. And I just want you to know, they've given you all the lever arms. They've given you the perpendicular components of the length of the wheelbarrow. And there they are. So yeah, so when you do this problem, all I got is F times 1.1 meters, and that's going to rotate it counterclockwise, so that's minus, and then plus 100 newtons times 0.3 meters equals 0, and so, you know, so I get my force, I get my answer there. So I want you to see it's valuable to understand this concept of lever arm, because it'll allow you to do problems where they don't tell you what theta is. I don't know, do you understand that in this case these lengths are my lever arms? They're the perpendicular distances to my lines of action. Oh, hey, let me give you another one. I gotta give you 2 more and then we'll be done. This problem is gonna help you do problem 17 on tonight's homework. I'm not gonna actually do the problem, I'm just gonna help you to understand it. This distance from there to there is 1 meter. This distance from here to here is 2 meters. This is your point of rotation. It's a uniform door.
Thank you.
So the center of mass is going to act, rather the weight of the door is going to act at the center of mass of the door. So here's the weight of the door. And here's another force, which I'll call F. And so relative to this point of rotation, I'd like everyone to please find the lever arm for the force F. Please do that right now. And I'll even give you a hint. L equals either 1 meter or 2 meters, and you've got to choose one of those. Which of those is my lever arm for F? And I'll make a recommendation, draw the line of action, and then draw the lever arm. Draw the segment, this would be great. Good luck.
The orange chair shocked me.
Oh, did it?
Yeah, I've been shocking myself a lot lately.
How interesting. Maybe it's just because of what you're wearing? Or maybe your shoes are really, like, making sure you're not grounded. You know, maybe those shoes are really isolating you from the ground. That's freaky. Wow. Yeah, it has to be your shoes. Your shoes must be really electrically isolating you. That's really freaky. The soles, maybe the soles are made of like some sort of PVC material. Some plastic. Yes, sure. If you can get past them. If you can't, then stop.
Sorry, Hannah.
Okay, well, hey, time's up. Here's the line of action. Boom, 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 boom. Here's the points of rotation. So I'm going to draw my lever arm from the point of rotation to the line of action. Let's have a vote. How many people say the lever arm is 1 meter? How many people say the lever arm is 2 meters? Okay, yay. Yay for each and every one of you. Yeah, it's 2 meters. This is the lever arm for that force F. That's the lever arm for F, and it's 2 meters. So if someone were to ask what the torque due to force F is, it'd be force times 2 meters. Here, let's do the last one. Now I'd like everyone to please find the lever arm for the weight of the door. And I'll give you 2 choices. That lever arm is either equal to 1/2 meter or 1 meter. Good luck. Draw the line of action and then draw the perpendicular segment from the point of rotation to the line of action.
I miss my chopsticks.
I was gonna say, no chopsticks.
Yeah. I forgot them at home.
Yeah, because yours are not the cheapo wooden ones. Those are really nice chopsticks. Alrighty. How many people say 1/2 meter? Okay, how many people say 1 meter? Okay, well, hey, the proof is in the pudding. Let's go ahead and make my line of action. You guys okay that that's the line of action for the weight? And let's go ahead and get the perpendicular distance from the point of rotation to the line of action.
Oh,
Are you guys okay that that's 1/2 meter?
okay.
So if someone wanted the torque exerted by that weight, it'd be weight times 1/2 meter. Okay, so you guys okay with that? Alrighty, well then, there's one more problem I need to show you. It's a problem like number 22 with a guy slouching against the wall. Okay. Here's a problem like number 22. Okay, so here's some guy slouching against the wall. It turns out that this is a 55-degree angle. This distance from the point where his slouchy back is contacting the wall to where his worthless, good-for-nothing feet are in contact with the ground is 1.5 meters. Okay, and it turns out that the center of gravity, or the center of mass of this guy, ends up being 0.9 meters away from his feet. There's another thing that makes this problem doable, and that is that the wall is what they call smooth. And when a physics problem says that a wall is smooth, that means it's frictionless. There's no friction between the guy's back and the wall for some crazy reason. Well, because it makes the problem much easier to do. So only force the wall exerts, the wall only exerts normal force on the guy's back, no friction. However, the feet are a different story. Feet, they get normal force and friction force, static friction force. There is a type of wall that's frictionless. It'd be a wall made of wet ice.
Huh?
And there's actually a science museum I went to where they had that. They had a wall made of wet ice, which means if you like try to lean against the wall, you're really taking a risk because there's no friction. So you just slide and fall. And I think that's one in Southern California. Has anyone ever seen that? Anyone seen a wall, a ice wall? Have you? Yeah, I don't remember where it was, but it was really cool. I remember showing it to my son or daughter or something where I had a book and I pressed the book up against the ice wall and the book just slid down. Like there's no friction there. So no matter how hard I push, I can't keep that book up on the ice wall because there's no friction. So it is kind of cool to have an ice wall. Like I said, just don't lean against it. You'll slide off and hurt yourself. Okay. So let's go ahead and do a free body diagram. Here's slouchy guy. This is a 55-degree angle. I'd like everyone to please go ahead and make this free body diagram. I'll give you a minute. Put the forces, label this free body diagram with the forces. Let's see how many of them you guys figure out. For slouchy guy.
Was the room cold that they had the wet ice?
Yeah, not particularly cold, but it was, I think it was cold because of the presence of the wet ice wall.
Oh.
But I don't know. No, I don't remember it being like in an ice rink or, something like that sort of thing. Where ooh. No, it just happened to be there. Yeah. Wet ice wall.
Would a wall completely made out of Teflon be frictionless?
Yeah, or close to it, absolutely. Same idea. Yeah. Alrighty. Well, hey, Did you guys get this normal force right there? The normal force the wall exerts on his back? And we've got this 550 Newton guy. Did I tell you he weighs 550? Oh, I didn't tell you that. Oh, I'm so sorry. Shoot. Dude weighs 550 Newton. So if you were putting his weight here, that would be fine. But it turns out that actually you can assign a number to it. It's 550 Newtons. And then finally, what forces are acting at his feet? Good, friction. And since his feet want to slide that way, friction is going to be this way. And what's the other force? You guys think of normal force?
Yeah.
So I'm going to call this normal force number 1 and normal force number 2, since I got 2 different normal forces, but I have to distinguish them. Okay. Now, remember the book? The book's torque equals force times distance times sine of theta. Will I be able to use that on this problem? Well, let me label it. You know, from here to here is 1.5 meters, and then from here to here is 0.9 meters. Will I be able to use that formula on this problem? What do you think? There's something about this problem that tells me yes. What is it about this problem that says, yeah, I will be able to use that crazy formula? What have they given me?
Angle measure?
Yeah, they gave me the angle measure. So if there's some way of finding the angle, then yeah, if you prefer, just mindlessly use the formula. But if they don't give you the angle, then then quite often you're stuck having to do your cleverness with the lever arm. Okay, and here's the last question I'm probably going to ask you guys. Tell me, which of these 3 points should I take my torques about? This point, or that point?
That one.
How many people say this point? How many people say this point? How many people say that point? Okay. Yeah, why? Why is this a good choice?
Because you have 2 unknowns.
Yeah, because it has 2 unknowns. Let's get rid of both of those unknowns. So I'll call that point A. And so I'll have the sum of the torques equals 0. And so now I have to get the torque exerted by this guy. And if you're someone who likes to just do the book, if that's a 55-degree angle, tell me what's this angle here going to be? Hopefully you're getting 35 degrees. Okay, so I'm going to define counterclockwise as positive, so this tends to rotate it counterclockwise. So I've got 550 newtons times 0.9 meters times the sine of 35 degrees, because that's the angle between the force and the lever. Now, if you're a lever arm sort of guy, if you like to draw your line of action and then get your lever arm, then you would have ended up with 0.9 times the cosine of 55. And that'd be the same thing. 0.9 sine 35, 0.9 cosine 55, it's all good. Finally, this normal force rotates it clockwise. So that's going to be minus that guy times this lever arm, or just get this. What's this angle here going to be? How good are you guys at geometry? And what's that angle? If you're thinking 55, you win. So it'll be this guy times 1.5 times the sine of 55. I'm just doing this problem as if I was the type of person who loved using that formula. And so you can just use that formula. Just make sure every angle is the angle between the force and the lever, you know? And so just trust me, I get this ends up equaling 231 newtons. Whoops. 231 newtons. Okay? So you tell me, how am I going to find Fm2 and Fs? And this is the last question I'll ask you, I promise. What equation should I use to find Fm2, let's say? Is anyone looking like at my agenda and like thinking that I might be?
Do you not have to?
Is anyone thinking do some of the forces in the x and y direction?
Oh my god.
Yes.
Okay, good. Well, that's what I want you to do. Sum of the forces in the y direction equals 0. And the y direction, what do I got? 550 down and Fn2 up, right? I got Fn2 minus 550 newtons equals 0. So normal force 2 is equal to 550. No need to do any torques now. The force equations are just too darn easy. And the sum of the forces in the x direction equals 0. Well, hey, I got that guy, and that's all I got. You know, I got the 231 newtons, and I got the static friction force. So the static friction force is 231 newtons. You see? So once you use a torque equation to find one of the unknowns, just do sum of the forces to find the others, and you'll be fine. You know? In fact, you could have gotten what Fn2 was without even doing anything. You could have just looked at the problem and said, well, I know these two forces have to be equal and opposite. So Fn2 is 550 regardless. And then once you made that determination, you could have chosen this point as the point of rotation. You know, that would have been fine. All right. Well, anyway, hey, this is like problem 22. I hope you're ready to do a problem like 22 or 17 or 15. Or 19 or 21. Any other questions or issues? Well, good luck. Lever arm. Bye-bye.